Right. So let's discuss a problem, right, based on crossed bell drive systems, right. So I will underline this one. Crossed bell drive systems, right. Right. So now let's carefully read the problem and understand all the concepts, right. Because when you are solving this type of a problem, right, so there are certain things, certain important equations that you must know, right. Because the reason in the examination, right, you will not get these equations, right. So there will not be any sort of a formula sheet, right. So be very careful, right. So what is the problem, right? So let's try to understand the problem while we are reading, right. A solid shaft that operates at 250 rpm, right, is used to drive another shaft that rotates at 350 rpm. So now, what is the meaning of that? So that means a shaft that is rotating at 250 rpm is used to drive another shaft that rotates at 350 rpm. So that means it is so clear that this side must be the input side, right, and this side is the output side, and that is one thing, right. And also we know that when we are solving this type of questions, right, so there are certain set of basic equations that we must know, right. One equation is that we know that the ratio of the RPMs, right. So let's call it N1 divided by N2, right. So sometimes N1 can be the input RPM or whatever. So as for now, just for remembering purpose, right. So let's say that N1 divided by N2 equals what? So that equals the ratio of the diameters in the other way around, right. So we can call it D2 divided by D1, right. N1 divided by N2 equals D2 divided by D1, and that is one thing. So now what is this one? So this is a cross bell drive system, right. So if you are going to consider a cross bell drive system, that is one feature that you should know. If you are going to consider the angle of lap, right. What is this? The angle of lap when considering, either you can consider that from the smaller pulley, right, or either you can consider that from the larger pulley, right. Whatever the type of the pulley that you are going to consider for this, right, it will be the same, right. Even if you consider the angle of lap from the smaller pulley or even from the larger pulley, so both will be the same, right. That is one thing. All right. So now, so let's sketch this one. All right. So now I am going to sketch the pulleys, right. So now you know that based upon that equation, right, input 250 rpm, that means definitely this side diameter must be the higher diameter. So let's say you don't have to write these things, right, but just for teaching purpose, right. So this side we can say the higher diameter. Why? Because low rpm there, right. So then this side lower diameter, right. So now, so let's sketch the bell drive system. So higher, so this is the pulley with the larger diameter and this is the smaller pulley, right. Okay, right. So now I am going to sketch the belt. So now we have to attach that belt. So before that, now this is the center of the larger pulley, this is the center of the smaller pulley, right. So I have sketched the vertical center lines, all right. Now, so this is how the belt goes, all right. All right. I hope that is clear. Now I am going to mark some important points, right. Don't get confused, right. 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 So now let me teach you actually what are these points, right. So just consider this particular point here. So this is that particular point, right, where this belt, so this is the belt, right. So this is that particular point, right, where the belt is going to leave the pulley, right. So where that particular contact breaks, right. So at this particular point, right, the belt is going to leave the pulley, right. Belt leaves the pulley, right. So this point, and here also the same concept, and here also the same concept, and here also the same concept, right. So measured from the vertical center line, right? So let's say that angle is alpha. So we have this angle alpha, right? Alpha, right? So if it is not clear on the board, right? So I will sketch the same thing, right? Here, right? What is this one? The vertical center line, right? What is this point? That particular point where this belt is going to leave the pulley, and here also we have that same point, right? So, right? So what is this angle? So this is alpha, right? Alpha, right? So I hope that is clear, right? So now, that is what I am telling, when considering this type of problems, right? There are certain facts that you should remember, right? So now, considering this alpha, there is an equation. So I need the calculator also, right? Now, so there is an equation for, in order to find this alpha, right? So the equation is, right? So I will write it here, right? So sin alpha equals the summation of the pulley diameters, right? D1 plus D2, the summation of the pulley diameters divided by 2x. What is this x? X is the distance between the shaft centers, right? So how can I, now here we have the shaft center, right? The center of that particular shaft, because we know that this pulley, right? Both of these pulleys, right? Both of these pulleys are connected to a shaft, right? So there is a particular distance x between the shaft centers, right? Right? Where these pulleys are connected, right? So let's call it x. So distance between these centers, right? So what is that? So that is x. I will mark it here. So what is this distance? So that is x, right? I hope that concept is clear, right? Or even here, I will just erase this for some time, right? So distance between that x, all right? Okay, all right. So then what are the other information, right? It is given that belt is 120 millimeter. What is the width of the belt? So I will write all the given parameters. See, what is the width of the belt? W equals 120 mm. What is the thickness? Simple T. What is that? So that will be 10 millimeter. All right. It is given that the distance between the two shaft centers is maintained at 4.8 meters, right? So what is 4.8 meters? So that is actually x, right? So x is 4.8 meters. What is that? The distance between the shaft centers, right? So that is actually 6 times the diameter of the smaller pulley, right? So this x is actually 6 times the diameter of the smaller pulley, right? So x is 4.8, 6 times diameter of the smaller pulley, right? So what is the diameter of the smaller pulley now? 4.8 divided by 6. So answer is 0.8 meters. So now actually what is the 0.8 meters? So smaller pulley, right, belongs, right, the smaller pulley belongs to the output pulley. What is the reason? Because that RPM is the largest, right? All right. So actually then we can better say, what is this 0.8 meters? So that is actually D2. D2 equals 0.8 meters, because our notations are going like that. So we say that D1 and N1, that these variables D1 and N1, these variables belong to the input side, right? Or we can say the driving side, right? And we can say D2 and, you can put a comma, D2 and 2, they belong to the output side, right? Output side. What is the output side? Or the driven side, right? So now we know that here 250 RPM, a solid shaft that operates at 250 rpm is used to drive another shaft at 350, because now we know this important equation also, right? So if we say N1, right, if we use this subscript 1 for the input side, right? So N1, D1, they belong to the input, then D2, N2, they belong to the output, right? So now here we know that N1 is the low RPM, right? N2 is the highest RPM, right? So now we know that what is our N2? 350 RPM. What is N1? That is 250 RPM. So now then what must be this 0.8? So 0.8 must be the pulley diameter of the output side. So D2 equals 0.8 in meters. Alright, I hope that is clear, right? Now we can use this equation and we can find what is D1, right? Or the pulley diameter of the input pulley, right? Or we can say the larger pulley, right? Okay. So N1 divided by N2 equals D2 divided by D1, alright? So subject D1, right? So D1 equals what? D2 times N2 divided by N1. So what is D2? So that is 0.8 multiplied by 350 multiplied by 250. So what will be the answer? 50 times 5, 50 times 7, alright, 5.6 divided by 5. 5.6, if you divide by 5, right, what must be the answer? So that must be what? 1.12 meters. Is that correct? Right. So then sin alpha equals D1 1.12 plus 0.8 divided by twice 4.8. Alright, so now let's find what is alpha. So alpha equals sine inverse what you will be having here. So let's use the calculator. Alright, so what is this? 11.536. We can simplify this, let's say 11.54, but be very careful. So now here this 11.54 is in degrees, right? Be very careful. So now we have calculated what is alpha. 11.54 in degrees. Be very careful. Correct. So now let's consider what is this angle of lap. So actually the angle of lap is that particular angle where this pulley, right, either it may be the larger pulley or the smaller pulley, right? So that is that particular angle where this pulley is actually covered or wrapped, right? Where this pulley is actually covered or wrapped, right, by this belt, right? So because if you are going to consider this belt, right, so now see that, so these 2 points are the couple of points, right, where this belt actually is going to leave the pulley, right? So considering that, angle of lap is that particular region where this pulley is actually covered or touched or wrapped by the belt, right? See, something like that, right? So what is that angle, right? So that is actually 180 degrees, right? Because you know that from here to here we have 180 degrees, right? Plus one alpha from there and another alpha from there, right? So if you say that angle of lap is actually theta, what is that? 180 degrees plus 2i is alpha, right? So 180 degrees plus twice alpha. What is alpha? We have already calculated from there, right? So that is 11.54, right? Degrees, right? So then what is theta now? 180 plus twice 11.54, right? 203.08. But be very careful, this is in degrees, right? You need to convert this value into radians, right? Because what is the reason? Because here that's a very important equation that we are going to use. What is that? So that equation is actually the ratio of the driving tensions, right? T1 divided by T2 equals e to the power mu theta, because we are going to use this equation, right? T1 is the highest tension or the tension at the tight side, right? T2 is the tension at the slack side, right? That is why we need to evaluate this theta here, right? But be very careful, this theta must be given in radians, not in degrees, right? So now how can we convert this value into radians? Pi radians equals 180 degrees, right? So what you can do is 203.08 divided by 180 multiplied by 5. So what is that value? 3.5. I'll just write it here. 3.5444, like that, right? So better say theta equals 3.54 in radians, right? You are okay with the angle of flare, right? So now what is the next thing, right? So now we are going to use this equation that is based on the ratio of driving tensions, right? So that is T1 divided by T2 equals e to the power mu theta, right? Because what is our target, right? We have to find the stress that is developed in the belt, right? Because we need to find that, right? So now for that there are certain equations that we have to use, right? So this is a one equation, right, that you must definitely know, right? And you can also use this equation as well. What is that? 2.3 log T1 divided by T2 equals mu theta, right? Or you can either use this one, right? But I am going with the equation that I have labeled under 1, right? Right. So now, do we know T1, right? We don't know T1. We don't know T2 also, right? E to the power. What is our mu? As it is mentioned by the question, right? So that is 0.35, right? So which is the coefficient of friction between the belt and the pulley, right? So what is theta, right? Be very careful. 3.54, right? So again you need the calculator, right? So if you carefully do the calculations, right? Right, e to the power, right? 0.35 multiplied by 3.54. We have 3.45. T1 divided by T2 equals 3.45. So that is a one equation, right? T1 divided by T2 equals 3.45. Alright. So let's study about the concept of tight side tension, right? Tight side tension. Alright. So now let's consider this pulley, right? So now, and this is the belt, right? So now this pulley is rotating towards the clockwise direction, right? So because of this clockwise direction of rotation, right, this upper part of the belt, right? So let's say this is the part of the belt at upside, right? And this is the part of the belt at downside, right? So let's select that, right? So because of this clockwise rotation, right, the upper part will feel or will undergo a pulling force, right? Because of this rotation, right? So this part of the belt will feel kind of a pulling force, right? So because of that, this side will get tightened, right? right? So this side will get tightened, right? So that is why here we call it tight side tension, right? So what is that? Tight side tension. So the opposite scenario will happen to the lower side, slack side tension, right? So just wanted to, alright. So the next equation that we are going to use is, that is the difference between the driving tensions, which is T1 minus T2, right? Where T1 is the tension at the tight side and T2 is the tension at the slack side, right? Times the velocity of the belt equals the power transmitted by this belt drive system, right? So let's call it P, right? So now here we need to find this belt velocity V, right? So what is V? Belt velocity, right? For that there is an equation. What is that? Either it is pi times d1 times n1 divided by 60, or pi times d2 times n2 times divided by 60, right? So you can use whatever the equation, but be very careful, right? So let's select this one, pi d1 n1 divided by 60, right? So pi times, now what is our d1? Our d1 is 1.12 meters. What is the RPM n1? So that you must actually remember. So the higher diameter means that is the low RPM, 250 divided by 60, right? So what is the value? Pi times 1.12 multiplied by 250 divided by 60. 14.66. What is the unit? Meters per second, right? Alright. So now we can continue with this equation, right? So T1 minus T2 times 14.66, right, in meters per second. What is the power transmitted by this belt drive system, right? That is 7 kilowatts. With proper units we have to keep in watts, right? 7 kilowatts means 7,000 in watts, right? So then what is T1 minus T2? 7,000 divided by 14.66, right? So 7,000 divided by 14.66, 477.49, right? So now we can write the other relationship, right? T1 minus T2 equals, right, 477.49, right? So now with this one, right, so now we already know a couple of relationships, right? The next target is to find the tension at the tight side, right? Because now what is the question? The question is that we need to find the stress developed in the belt, right? The stress that is developed in the belt. So what is the equation for that? So that is tension at the tight side divided by width of the belt multiplied by the thickness of the belt, right? So for that we need to find what is the value of T1, right? So we need to find the value of T1, right? So let's, from this one we have one equation, T1 divided by T2 equals 3.45, right? So from that we can subject T2. So what is T2? T1 divided by 3.45, right? So this relationship we can use in the second equation. Alright. T1 minus T2 equals 477.49, right? Simplification, right? So T1 minus 3.45, 477.49, alright. So now 3.45 times T1 minus T1 divided by 3.45. I'm writing all the steps, right? But you must know all these steps. So then this minus that, 3.45 T1 minus T1 will be 2.45 T1 equals the product of this 3.41 times 477.49. So let's do that. 477.49 multiplied by 3.45, 1647.34 equals this value 2.45 times T1, right? So what is T1? So T1 will be 1647.34 divided by 2.45. Right. 672.38. So now what is our T1? Now T1 we have calculated, right? So what is that? 672.38 in newtons, right? I hope that is clear, right? So now what is the value of the width? So that is 120 millimeters, right? So you can say 0.12 meters, no problem, right? So we'll convert the value into meters, right? So then thickness 10 millimeters. What is that? That is 0.01 meters, right? So let's continue, right? So here we can have the final answer, right? So now 672.38 divided by 0.12 multiplied by 0.01. The answer is 560,316.67 in newtons per meter squared, right? So that's kind of a larger value, right? So what you can do is, right, either you can keep that in. Now see, now here we already know, right? If I go to consider newtons per meter squared, so that is equivalent to pascals, right? What does it matter even if you keep the answer like that? No worries, right? Newtons per meter squared equals what? Pascals, right? So if you take 1, 2, 3, 4, 5, 6 decimals towards the left side, so you can call it 0.56 what? Megapascals, right? Right? 0.56, right? Megapascals, right? So either you can keep the final answer like that. So this is the stress that is developed in this belter system, right? So that is the stress that is developed in the belter. All right. So thank you very much.